This is rolling. All right. So this is our last lecture, and we'll have the exam next Wednesday. Excuse me. Thanks. Yeah, we'll start that at 4 o'clock, and it's scheduled for 2 hours, so we'll actually finish 20 minutes early compared to what we're usually supposed to go to for our once-a-week class schedule. The pattern of the exam is going to be the same as what we've done already, where there will be a concept question section, and then on the concepts you just are writing from your mind and your memory using the pencil or pen, and then in the problem solving is where you may have problem solving questions related to computer stuff. You can bring a page of notes to use on the second part of the exam. Now, the first exam was so computer heavy that I think that there won't, I'll eliminate the suspense for you. We won't do StormCAD or HY8. So I will ask a WMS question, and it will also be useful for you to have access to Excel. All right. So the last topic for the course is just a single lecture on groundwater, and unfortunately there won't be an opportunity for you to do a homework assignment related to groundwater. But I guess I should have included the announcement about the project. That's also due next week. Remember, the report is due at the beginning of the class meeting next week. So project report due Wednesday.
And you'll have, I mean, you might already have it. You have a Blackboard upload file. You might already have it.
Oh, you mean like a location to upload it to?
Yeah, like the homework, same concept.
Yeah, good question. Yeah, that is what it'll be. I don't recall whether I've created it or not. All right, but I'll be sure that I do that. So any questions about what's going on between now and next Wednesday? All right. Groundwater hydrology is a huge topic, and it could easily take up not just one course at the graduate level, but an entire course of study. And in fact, when I was in grad school, there were people who were doing just that. You know, at the PhD level, they were taking all of their coursework to talk about the movement of water underground, and they were also doing their research on it as well. And what we're going to do today is just scratch the surface, and it may be some things that you've seen before, like Darcy's law is pretty familiar to most people. The well equations, sometimes that is new to folks. Have you seen, like, oh good, yeah, it's great to become familiar with those, because although they don't, at least at the FE level, those questions don't take into account variations of soil underground. It's just assuming a homogeneous dispersion of the soil. It's still kind of interesting, I think. So there are really sophisticated ways to model the movement of water underground. And if you break the underground environment into finite elements where there's a mesh and cells, each one of which has its own hydraulic conductivity and other properties that that characterize the movement of the water, then you can come up with three-dimensional plots like this, where it's a model of resistivity of soil. It's just kind of easy to measure resistivity. So that's why it would be measured as a proxy for pollutants. And so this is a key area, a nexus area for environmental engineering and hydrology, because a lot of the reasons why we're interested in the movement of water underground may be related to water production, but sometimes it's also related to contaminated soil, where in the past history up through the 60s, and in some cases as late as the 70s, it was pretty common for businesses to land apply leftover chemicals like PCBs, which were used in transformers as an insulating fluid and are really harmful to human health. Another pretty common underground pollutant is trichloroethylene, which was used as a dry cleaning fluid. And when I was a grad student, we went and looked at a location that was contaminated with explosives in the soil. Explosives that were made during World War II are still being filtered out of the drinking water in this little town called Mapleton, Utah. So it's kind of interesting how long these problems can last, because when the contaminant gets down into the soil, it just disperses like crazy.
Yeah, where I work at in Charleston, there's carbide plants across the river, and there's several flares floating around that we actually have to, I think, prevent for mitigation.
Yeah. Yeah. And I've noticed here in Huntington, there's a gas station that's on the corner of Hal Greer and I forget the name of it, but it's like a Clark's Pump and Shop or something like that. And there's been some environmental remediation truck constantly parked over there, and it kind of looks like they might be doing some soil vapor extraction or venting or something. So there's probably a lot more plumes than we recognize. There's some of the big ones, like at a big chemical plant, but then I think even on the smaller scale, it can be something as seemingly innocuous as a gasoline station that is going to be really expensive to mitigate. Another reason why subsurface hydrology is so important is because it's a huge fraction of the fresh water that exists on our planet. Now, most of the H2O on planet Earth is in the oceans, and it's challenging to use that water. I mean, it can be done through thermal distillation, through desalination, by membrane technologies, but the cost of producing a cubic meter of water from the ocean, I think at best is in the range of maybe about 50 cents per cubic meter. And they're always working to get that a little bit lower, but anyways, it gives you a scale, at least, like a ballpark order of magnitude estimate of the cost of generating water from the sea. In contrast to that, it's exponentially less expensive to just pump water from the subsurface environment. And so the advantages of doing that is, number one, most of the groundwater, unless it's under the influence of the ocean or another saline sea, the water in a lot of cases is fresh and can be used directly, especially if it's for irrigation, and there's no need to disinfect and coagulate and all that. You can just pump it out and irrigate with it. So if you look at this table, though, what it does is it differentiates between groundwater that's less than a kilometer underground and then groundwater that's more than a kilometer underground. And I think that they break it up into sections like that because there is a limit to how deep it's technically feasible to pump water. And more than a technical feasibility issue, it's really an economics issue where just the expense of lifting water a vertical kilometer would consume so much electricity that then maybe desalination becomes feasible again if you're having to pump water from that deep. So groundwater is an important water source, and this video that we're going to watch kind of highlights that point by identifying one of the most important aquifers in the United States, the Ogallala Aquifer, which kind of overlays with a lot of the Midwest agricultural regions. So I'm going to pause this video so it doesn't get booted off of YouTube. All right, so that video kind of gives an overview of some of the problems related to when there's more water going out than coming in to an aquifer. And an aquifer is a really great example of something that can be understood using principles of mass balance. You know, it's a storage area where, as they said in the video, water over thousands and tens of thousands of years has very slowly entered that storage area. That's the pores in between soil grains. And then just in a matter of seconds, with very powerful electrical pumps, that water can be extracted at a rate far greater than the annual recharge. And so during a period of drought, it's kind of a double whammy, because not only is there less recharge coming in, but at the same time there's also more demand, and so there's less in and more out. And that's why they were saying that the water levels have been falling by 2.1 feet per year during the droughts that started back in 2011. So frankly, I'm a little bit skeptical. That video was, I mean, as an engineer and scientist, it's always nice to see you know, research being done in the real world and using historical data to understand the problem better. But in this case, the problem isn't that we don't understand. Like The issue isn't we don't understand it well enough. It's very simple. The issue is that there's an economic demand for the products that can be produced when you pump water from the aquifer. And so as long as farmers are going to get more money with their crops, then it costs them to pump the water out, and they're going to keep pumping.
That's why I thought when you want farmers to benefit, they'll share or reduce or whatever, but yeah, until you're
Yeah.
you're
It's the tragedy of the commons. You want everyone else to conserve, but then your economic incentive is to use as much as possible, because if they're using less water, then that means there's going to be less crops, and it drives up the prices, and then you have personally an added incentive to maximize the amount that you can grow. So in the West, they seem to have more effective water use restrictions where there's a water law system where you actually have a legal right to only a certain amount of water that can be extracted from streams. But that's water, surface water. And water rights in the eastern part of the United States and in the Midwest are totally different than the water laws that they've developed in the West. And
what's the line for the West, like Colorado and West, or would you say?
I think so, yeah. But east of that, this Ogallala aquifer extends into eastern Colorado. It's just he who has the biggest pump can pump the most water. So, all right. And let's just take a quick look at one very low-tech effort to increase the amount of groundwater recharge. Okay, so if we think about what's happening there, it's increasing recharge compared to the recharge that normally would occur for a couple of different reasons. I mean, it's just as simple as digging a hole, but the reason why we have enhanced recharge there is there's a couple of things we've talked about infiltration before. When we were discussing the infiltration just in kind of the general principles of hydrology. One of the principles we learned is that the depth of water at the surface is one of the driving factors that pushes water through the soil. And so like when we were doing the green amped model, what we assumed is continuous ponding at the surface. And so how deep the water is, that's kind of the driving force that pushes the water into the pores. And so at the surface, there's a couple of things that interfere with that. Number one, if the water is spread out over a field, like we kind of see at the beginning of this, I think, did it show us I thought at some point it showed the field from more of oh, there we go, yeah. All right, so this field in the surrounding area, it's very shallow. And if there is silt or clay, like fine suspended particles, then those clays are going to settle down and it's going to clog the pores. And so number one, you've got really small pores for the water to be getting into. And number two, it's relatively shallow, and so there's a small driving force. In contrast, when they use something like this, the depth of water, let's say for instance that the water table is here. If they've got water all the way here, now there's a greater delta H, the driving force that's pushing water into the soil is going to be relatively larger. And so that delta H is bigger than if it was just ponding at the surface. The other opportunity that they have, although I'm not sure if they're taking that opportunity here, it looks like this ring around the edge could feasibly be used to skim pollutants so that you have cleaner water going into the recharge well. And so like best case, what they'd be doing is they'd be filtering the sediment out so that this mesh, the screen inside of the well casing, doesn't become clogged with the turbidity and the clays and the silt that's in the water itself. So it kind of overcomes a couple of the barriers to increased recharge. Here's a cross-sectional view that will help to define a couple of terms. An aquifer is just a significant amount of water that's captured in the underground environment where it can be withdrawn, and aquifer usually is talking about the saturated zone. I mean, there's water in all soil, It's just that above the saturated zone, it exists as soil moisture that's bound to the outside of the grains, and it's not easily extracted until all of the voids are full and there's no air in the voids. So this is showing an unconfined aquifer where the water above the water level is the vadose zone, or the zone of aeration as it's called. But the confined aquifer is pressurized, and what makes it pressurized is this crosshatched area is illustrating a impervious formation, like maybe a clay layer or a rock layer, but for whatever reason there's this layer of really low hydraulic conductivity on top and on bottom, and then there's some recharge. If you go away from this confined area, there's recharge somewhere else that's causing the water table to be higher than it ordinarily would be if it wasn't for kind of like this funnel formation that's guiding the water downward. And so you can kind of think of it as a tank, in other words. I mean, like, forgetting the fact that this is a soil area, if it was just a water storage tank, then you can see that anytime the casing punctures that upper confining layer, the water has the potential to flow free. And that's what this artesian well is. When the well casing goes all the way to the surface and there's enough pressure in the confined layer that it flows freely, and that's an artesian well. Now sometimes it'll make it most of the way to the surface, but not all the way. It all depends on the piezometric pressure there. So let's see, I'm keeping an eye on the time here. I think we've got time to consider this, this video that I found just today that kind of someone's done some experiments to show what happens when you drain a confined and an unconfined layer. So let's watch that. Oops. It's like I've never used Windows before. There we go. All right, so it was actually this section that I thought was kind of the most applicable visualization of what we're going to be calculating today. I mean, I've got a couple of diagrams, and we're going to be using a formula that actually calculates the flow rate that's coming out as a function of what the cone of depression is doing. That cone of depression in an unconfined aquifer is what we could measure with a monitoring well to know what the pressure is inside of the aquifer, and it's that pressure that's the driving force of the water towards the well casing. And he also talked about how in the confined section it's a similar thing, although it's not a physical water surface, but rather it is the pressure surface, and so the phreatic surface, and we'll go over the equations for that. So artesian is when it flows freely at the surface because the ground level is lower than the piezometric elevation. An aquitard, in that video he used that phrase, and that is just any layer that's slowing down the water's movement. And then a leaky aquifer is when there is a semi-pervious layer, meaning just that the hydraulic conductivity is relatively low, but it's not maybe as low as rock or clay would be. Sometimes an aquifer can leak as well if it has a rock layer that's fractured. So there can be both an unconfined leaky aquifer and a confined leaky aquifer, and in fact the leakage can happen upwards. If it's a confined aquifer, and if there were fractures in this layer, it could possibly be that the water is leaking upward. And we saw that same thing in the video where he had, a kind of, let's see, where was it, that he was complaining about the water bubbling to the surface, and he just kind of jammed it back down with his finger again. But, the water was leaking upwards. So that was a good illustration of that as well. All right, Darcy's law is probably, well, it's one of the most important equations that we've got for describing the flow of water through a homogeneous soil media. And I've seen a lot of diagrams. In fact, I think I've showed you some diagrams with Darcy's law where this column is vertically oriented. And for me, those have never made as much sense as in this diagram, where you move the column onto its side and you can kind of disassociate the movement of the water with any effect that gravity might be having, because it's genuinely, it's not gravity that's driving the flow of water through a packed column, but the driving force instead is related to the difference in the piezometric water pressure in the upstream end versus the downstream end. So there is an equation with a proportionality factor, that is the hydraulic conductivity, that relates for some cross-sectional area and the driving force. And so this delta H divided by L, you can think of it as the energy grade line or the hydraulic grade line. In other words, it's the driving force over some length. And we can get the flow rate of water through a packed column by knowing what's in there. And these hydraulic conductivity properties have been accurately described for a whole range of soils. And just kind of as another refresher on how to use Darcy's law, let's take a look at this example where we know the diameter of the column is 50 centimeters. The length between the upstream and the downstream piezometer is 2.5 meters. And we've got measurements of the water elevation at both sections. And so let's go through the process of calculating in a day how many liters is going to flow through this column. And this is the sort of thing that we could build in the lab. And if we have sand and if we have a 50 centimeter diameter tube, then we could pretty easily construct this. But the question is, how much water would we maybe expect to see in a 24-hour period? So I'm going to pause the recording. All right, so we've got a column that's 2.5 meters long. We're given the diameter, and so from that we can calculate the cross-sectional area. We get the K value for the sand out of the table, being sure to use the SI version of it rather than the traditional units. And then the delta H is just defined by the difference in elevations for the upstream and the downstream component. And the units that we're going to get when we put it into Darcy's equation are going to be cubic meters per second. And so if we want to convert that into liters per day, then of course we have to multiply by 86,400 seconds per day and 1,000 liters in a cubic meter. So, good, good. Yeah, that's one of my favorite ways to catch students is with the little units conversion at the end. Yeah. It seems like sometimes, especially like on the licensing exams, that they're emphasizing the unit conversions quite a lot. Have you already taken the PE test?
I'm going to in October.
Oh.
I think ENVE passed it, so.
Good. All right, so the cone of depression was illustrated during that video, and here is a figure that comes from our text that kind of shows what's happening, that as the water approaches the well, there has to be a reason for it to flow radially towards the center location. The pump, which is at the surface, the motor usually is at the surface, the pump will be down below. It's extracting the water, and it's kind of a simultaneous thing where you take a liter of water out of the underground environment, then there's going to be just a temporary depression. And that depression, because you've removed some water, well, it's going to be the water from surrounding areas is going to look at, there's a low spot in the energy. You know, water flows downhill, and that happens whether it's above ground or below ground. And so the downhill area is inside of the well casing. When you take a liter of water out, suddenly that water level inside the water casing is lower than the water in the surrounding soil. And so it reacts more slowly in the underground environment than it would if it was just like a lake that we are extracting water from. And so what happens is the water is gradually moving in the direction of the lowest energy level. And you can see in this diagram they're showing the well screening. Generally, just to simplify the calculations, we assume that a well is fully penetrating down to the entire, through the entire aquifer and to the bottom of the aquifer where we have a confining layer. And the distance between where the water level used to be before pumping occurred and now where the water level is during pumping is drawdown. And so the shape is that as you get closer and closer to the well, that the drawdown is greatest. And the distance away that you can go and still see some drawdown is known as the radius of influence. So there are equations that relate how much of a drawdown for a certain soil type is going to correspond to a certain extraction flow rate Q. And in order to measure this cone of depression, we have to have other secondary wells dug. And so this is a production well that we're seeing where the water is actually being removed from the aquifer. But to be able to see the cone of depression, we either have to have a glass window like they did in the video, or more realistically, if we have monitoring wells at a couple of different locations and we're able to measure how deep is the water level in those spots, then we can kind of extrapolate just from 2 measurements, we can find out what the flow rate is. And in fact, one of the measurements can be at the well casing itself. So we really only need 1 monitoring well besides the production well to be able to use the equations that we're going to go over. So there's a couple of effects that are illustrated here, and one is looking at the hydraulic conductivity of the soil. And so obviously in the case of a coarse gravel, the water can flow more easily towards the well, and so there doesn't have to be as much drawdown for the same flow rate. And in both of these diagrams, what we're seeing is, let's assume a constant flow rate from the one on the left and the one on the right. Maybe just for purposes of illustration, we're extracting 1 liter per second from both of them. But for 1 liter a second to move through the coarse gravel, you don't have to have as much drawdown because the hydraulic conductivity is higher. Whereas in the case of the sand, there has to be more drawdown to provide enough of an energy drop that is going to cause the water to flow through those smaller pores. Remember, the continually connected system of pores in the underground environment is a little bit like a pipe. And a small diameter pipe is going to have larger head loss. And so what we're saying is that there's more head loss as the water flows through the sand to get to the well than there is in the relatively larger voids in the coarse gravel. So if we have overlapping cones of depression, so both of these are discharge wells, then what we would have seen from any one of them individually is magnified, and so it brings the overall cone of depression lower. This is showing what the cone of depression would look like just for well A, but if there's an adjacent well that is going to be causing influence with well A, then it has kind of an additive effect on the cone of depression. Some of the terms that you'll see in problems of this type is fully penetrating, which means that the well casing goes all the way down to the bottom of the aquifer. The screen is usually a slotted pipe that just maybe if it's a plastic pipe, it will have very small diameter cuts in it to allow the water to seep in through the pipe. And then the well radius is sometimes used as one of the distance terms in the well equations that we're going to look at. And so it's important to distinguish between the diameter of the pipe that the well is made out of and then the well radius, which is what we'll put in as one of the distance measurements when we're using the production equations. Transmissivity is the hydraulic conductivity K multiplied by the thickness of the aquifer. And in the case of a confined aquifer, we usually measure that height with a variable B, whereas an unconfined aquifer, the depth of the water from the bottom confining layer up to the vadose zone is H. Okay, so we've talked about hydraulic conductivity, and its units are units of length per time. The aquifer thickness, B, is going to have units of length. Transmissivity is the product of the conductivity and the aquifer thickness. Piezometric head is what we'll use for confined aquifers because we aren't actually going to be measuring a physical water surface, but we'll be measuring the phoretic surface, or kind of the surface that is described by the hydraulic grade line and the measurement of the pressure. And remember that when we're talking about water flowing through a porous medium, that some of the soil porosity may not be connected. So an example of that is lava rock. You know, lava rock has a lot of pores in it, but not all of those pores are connected, and so it's only those pores which have the ability to transmit water that are included in calculations of porosity. Okay, the confined case is the easiest of the two, and we're comparing an unconfined aquifer and a confined aquifer. They're very closely related, but strictly speaking, the confined aquifer calculations are a little bit easier. And the reason why I say it's easier is that we don't have to calculate a corrected height. It's just an actual measured height. So what you can see is the production of this water flowing through the well is going to be related to 2 pi. And remember that what we're looking at is a cross-sectional view, and actually it's a circular cone of depression. And so if we assume a homogeneous soil, like it's the same type of soil down here in the aquifer, if it's sand all the way through and the sand all has the same hydraulic conductivity, then it's going to look like a funnel, that cone of depression. But in this case, it's not a physical cone of depression, it's a piezometric surface. So the transmissivity will be the depth of the aquifer, so B multiplied by the hydraulic conductivity is how we get the transmissivity. And then what's really important is that there is a convention in assigning 1 versus 2. And it's really easy to just assume that those two things are interchangeable, but the way that the equation is set up, actually, location 1 will be the location that's closer to the center line of the pumping well, and 2 is the one that's further away. So it's just as it's pictured there. And so another thing that sometimes students make mistake is in the problem statement it will talk about drawdown. And so you'd have measured drawdown at location 1 and location 2. But if you look at the formula, it's not actually drawdown that goes into the formula, but it's the height of the water. So measuring from the bottom of the well up to where the water surface is, rather than the drawdown is from the initial piezometric surface to the water surface. And so drawdown is this distance, whereas what needs to go into the equation is h. So it's from the bottom to the water surface. So those are some of the potential points of confusion that I've seen in the past. And so sometimes in a problem statement they'll be measuring the depth of the water at the well. And so you could just use location 1 would be at the well, and the radius that you'd put into this equation would just be half the diameter of the well. And then the depth of the water would be your h1. And then at some other location, you're measuring the depth of the water as well as the distance away from the well to that location. So this is the equation for a confined aquifer. And this is what it looks like in the FE reference manual. Since you've already taken and passed the FE reference manual, by the way, they're coming up with a standardized manual for the PE exam. Though I don't know if it'll be in place by the time you take the PE exam. It may be, maybe a year after you take the PE. I don't think it'll be ready by November, but they are working on it, which will be nice because then you won't have to wheel in a wheelbarrow full of books. Yeah. So, theme equation looks the same in the FE as the textbook version of it that's presented. So let's practice using the confined aquifer equation here. We've got the hydraulic conductivity defined, 20 meters per day. Note the units here. We know the thickness of the aquifer, 6.6 meters. And then the initial piezometric surface. And so measuring from the bottom of this confining layer up to where the water elevation was before any pumping. So that initial height is 14.53. And what we want to know is what flow rate, Q, would be responsible for causing the piezometric surface to be as described here. So we've got radius 1 at 40 feet, and radius 2 is at 80, not feet, meters, at 85 meters. And then in the second part of this problem, we are going to take a look at solving for the same Q, solving for H1, where we're going to substitute in a different R1 value. And what's sometimes tricky about writing problems of this sort is that it's easy to write a problem that's not possible. You know, like where the flow rate and the radius doesn't match up. So let's take a look at this one. So we've got a K of 20. The depth of the aquifer is 6.6 meters. And this H of 14.53. If we go to the sketch, that's just the initial height from the bottom to the top. So 14.53 is that. And we want to find out the flow rate is H1 is 13.85. So 1 is the location that's closer. And the location that's closer is going to have more drawdown. So it's going to be the lower of the two numbers. R1 is 40 meters, R2 is 5. So flow rate is 506 cubic meters per day. That's pretty huge. I guess this hydraulic conductivity is a little bit on the high side of anything that would be observed in reality. But then if we have that same flow rate, the question is what would be the depth of the water at the well? So what we're doing is we're starting with this. Q is given, and we can use either one of these locations to be our location 2. We're going to say location 1 is at the well itself. So that means that R1 is going to be half the diameter of the well. And we're solving for H1. So we're just rearranging the equation to solve for H1 in terms of H2 and everything else. Now there is going to be a well problem on the final exam, and I won't tell you if it's going to be confined or unconfined, but even though we haven't had a chance to do a homework assignment on it, there will be a well-related problem, so I'm glad that you're taking good notes.
On the second part, we did half the radius.
Half the diameter.
Half diameter.
Yeah. Because what we're saying is that the location where we're measuring the water depth is inside the well itself. And so the radius, the distance from the center line of the well, will just be the outside of the pipe that's Ooh, I just realized this microphone was in my pocket. This has been really interesting to listen to.
Yeah, but the other one where it's outside, we just take the, we don't have to, like I said, we can take the full radius.
Yeah. And so we could have used either of these other locations. So in this problem, it was using the place where we've got 40 meters. But you could have put in the place where it is 85 meters, and you would have got the same answer as long as you used this as the H2. Uh-huh. Yeah. All right. So that is confined. Unconfined is a little bit different. Because you can see what you're doing is you're squaring the term where we're measuring the elevation. And the reason for that is that it's a little bit different. If you look at the path line that the water is following, in the case of a confined aquifer, the water is just flowing horizontally towards the well. But now in an unconfined aquifer, it's not just the piezometric surface that's experiencing a drawdown, but it's actually the water itself. And so the flow lines are going to be shaped in such a way that it kind of has an effect on the energy loss. The path is longer than it otherwise would have taken if it was a horizontal distance. And so the way that this equation kind of corrects for that in a simplistic way is by squaring the difference of each term and taking the difference as the driving force.
Yeah, that's almost it. So I thought I stuck it down.
Yeah. Right. Okay, so here is the version of Dupuy's formula in the FE reference manual. So same as what we had before, but notice that when we were working with the confined aquifer, we were using the transmissivity. Now, the transmissivity isn't in there. It's just the hydraulic conductivity. And so there isn't like a well thickness that's going in, but that's another reason why we're squaring these terms, is that the units wouldn't quite work out to get length cubed per time unless we were squaring this, because the units of K are length per time. And so if we want it to be length cubed per time, then we have to have another length term in there. So that's where we get it. And let's try that out in the unconfined aquifer. The flow rate is known, 0.4 cubic meters per second. And the way that they're describing the shape of the drawdown is they're saying that 50 meters from the well, the drawdown is 1 meter. So they're measuring from the initial phreatic surface down to where the water surface actually is. And then 100 meters from the well is 0.5 meters. So remember, that's not H. What we have to do is we have to find H1 and H2 from the initial saturated thickness. So H2 is going to be 24 meters minus 0.5. H1 is going to be 24 meters minus 1 meter. And then R1 will be 100 meters, R2 will be 50. So what we're trying to do in this case is calculate K, the unknown hydraulic conductivity. Okay, so the two things we want to know is the hydraulic conductivity, and then if we get closer to the well, what does the drawdown look like just 5 meters away from the center of the well? We both got the same hydraulic conductivity, and remember that what we were given was the drawdowns, and so we have to convert from drawdown to the water height. If the initial water height was 24, so we just do the algebra to rearrange in terms of the unknown K, make the substitution. We both got the hydraulic conductivity was 3.8 times 10 to the minus third. And then for the drawdown, sorry, that's a little bit sloppy, but 2.74 meters should be the drawdown. And the way that we do that is we know that I'm calling location 2, in this case, the place where it was a height of 23.5 meters, and that's at a radius of 100. You could have also done location 2 is at a radius of 50, and then you'd use, if you'd done that, H1 is 23. So you'll see the ratio of distances is 100 meters versus 5 meters. And we're solving for the unknown height, and I think it should be 21.26. And that kind of matches up with what we know to be reasonable, that the drawdown is going to be a lot more dramatic the closer you get. And so we're seeing a lot more drawdown where it was only half a meter when we were 100 meters out. At 50 meters of distance, the drawdown was down to 1 meter, and so it's going to be quite a lot further down as you approach the well. It's, that cone is getting more dramatically deeper. Good. All right. That's it. We are done for the semester. Congratulations, you made it through. Nope.
Okay.
So let's just, let's see, the final exam next week, 4, the project report also upload before 4, and let me know if you have any questions as you prepare for the test or as you are getting close to finalizing your project. If there's anything I can clarify or any questions you have as you're studying for the test, just let me know.